Chapter 13. AC Circuits. Exercises pages 304 to 305. Exercises Q1.1, page 304. Choose the correct option. If the RMS current in a 50 Hz AC circuit is 5A, the value of the current 1/300th of a second after its value becomes 0 is. Solution. Exercises Q1.2, page 304. Choose the correct option. A resistor of 500 ohms and inductance of 0.5 H is in series with an AC source which is given by V equals 1002 sin 1000 T. The power factor of the combination is. Solution. Exercises Q1.3, page 304. Choose the correct option. In a circuit L, C and R are connected in series with an alternating voltage of frequency F. The current leads the voltage by 450. The value of C is. Solution. Exercises Q1.4, page 304. Choose the correct option. In an AC circuit, E and I are given by E equals 150 sin 150 T, V and I equals 150 sin. The power dissipated in the circuit is 106 W2, 150 W3, 5625 W4. 0. Solution. Exercises Q1.5, page 304. Choose the correct option. In a series LCR circuit, the phase difference between the voltage and the current is 45 degrees. Then the power factor will be 0.6072, 0.7073, 0.8084. 1. Solution. Exercises Q2.1, page 304. Answer in brief. An electric lamp is connected in series with a capacitor and an AC source is glowing with a certain brightness. How does the brightness of the lamp change on increasing the capacitance? Solution. Exercises Q2.2, page 304. Answer in brief. The total impedance of a circuit decreases when a capacitor is added in series with λR. Explain why. Solution. Exercises Q2.3, page 304. Answer in brief. For a very high frequency AC supply, a capacitor behaves like a pure conductor. Why? Solution. The reactance of a capacitor is. Where F is the frequency of the AC supply and C is the capacitance of the capacitor. For very high frequency, F, XC is very small. Hence, for a very high frequency AC supply, a capacitor behaves like a pure conductor. Exercises Q2.4, page 304. Answer in brief. What is Wattles current? Solution. The current that does not lead to energy consumption, hence zero power consumption, is called wattless current. In the case of a purely inductive circuit or a purely capacitive circuit, the average power consumed over a complete cycle is zero and hence the corresponding alternating current in the circuit is called wattless current. Exercises Q2.5, page 304. Answer in brief. What is the natural frequency of the LC circuit? What is the reactance of this circuit at this frequency? Solution. The natural frequency of LC circuit is. Where L is the inductance and C is the capacitance. The reactance of this circuit at this frequency is. Exercises Q3, page 304. In a series LR circuit, XL equals R and power factor of the circuit is P1. When capacitor with capacitance C such that XL equals XC is put in series, the power factor becomes P2. Calculate P1, P2. Solution. Exercises Q4, page 304. When an AC source is connected to an ideal inductor, show that the average power supplied by the source over a complete cycle is zero. Solution. In an AC circuit containing only an ideal inductor, the current I lags behind the EMF E by a phase angle of pi2 radians. Here, for E equals E0 sin omega t, we have I equals I0 sin omega t pi2. Instantaneous power, P equals A equals E0 sin omega t I0 sin omega t cos pi 2 cos omega t sin pi 2. equals E0 I0 sin omega t cos omega t is cos pi 2 equals 0 and sin pi 2 equals 1. Average power over one cycle. Note: for reference, see the answer to Q6. The proof should be written as part of the answer. Exercises Q5, page 304. Prove that an ideal capacitor in an AC circuit does not dissipate power. Solution: in an AC circuit containing only an ideal capacitor, the current I leads the EMF E by a phase angle of pi 2 rad. Here, for E equals E0 sin Wt, we have I equals I0 sin omega t plus pi 2 instantaneous power, P equals A equals E0 sin omega t I0 sin omega t cos pi 2 plus cos omega t sin pi 2 equals E0 I0 sin omega t cos omega t is cos pi 2 equals 0 and sin pi 2 equals 1. Average power over one cycle, PAV. Exercises Q6, page 304. A. An EMF E equals E0 sin omega t applied to a series LCR circuit derives a current I equals I0 sin omega t in the circuit. Deduce the expression for the average power dissipated in the circuit. B. For circuits used for transporting electric power, a low power factor implies large power loss in transmission. Explain. Solution. Exercises Q7, page 304. A device Y is connected across an AC source of EMF E equals E0 sin omega t. The current through Y is given as I equals I0 sin omega t plus pi 2. A. Identify the device Y and write the expression for its reactance. B. Draw graphs showing a variation of EMF and current with time over one cycle of AC for Y. C. How does the reactance of the device Y vary with the frequency of the AC? Show graphically. D. Draw the phasor diagram for device Y. Solution. 1. The device Y is a capacitor. Its reactance is, where omega is the angular frequency of the applied EMF and C is the capacitance of the capacitor. 2. The phasor representing the peak EMF, E0, makes an angle Wt in an anti-clockwise direction with respect to the horizontal axis. As the current leads the voltage by 90 degrees, the phasor representing the peak current, I0, is turned 90 degrees anti-clockwise with respect to the phasor representing EMF E0. The projections of these phasors on the vertical axis give instantaneous values of E and I. Exercises Q8, page 305. Derive an expression for the impedance of an LCR circuit connected to an AC power supply. Solution. The following figure shows an inductor of inductance L, capacitor of capacitance C, a resistor of resistance R, key-can source power supply of alternating EMF E connected to form a dosed series circuit. LCR series circuit. We assume the inductor, capacitor and resistor to be ideal. As these are connected in series, at any instant, they carry the same current I equals I0 sin omega t. The voltage across the resistor, equals Re, is in phase with the current. The voltage across the inductor, L equals X Li, leads the current by pi 2 radians and that across the capacitor, EC equals XCI, lags behind the current by pi 2 radians. This is shown in the following phasor diagram. Exercises Q9, page 305. Compare resistance and reactance. Solution. 1. Resistance is opposition to flow of charge as current, and appears in a DC circuit as well as in an AC circuit. The term reactance appears only in an AC circuit. It occurs when an inductor and/or a capacitor is used. 2. In a purely resistive circuit, current and voltage are always in phase. When reactance is not zero, there is a non-zero phase difference between current and voltage. 3. Resistance does not depend on the frequency of AC. Reactance depends on the frequency of AC. In the case of an inductor, reactance increases linearly with frequency. In the case of a capacitor, reactance decreases as the frequency of AC increases. It is inversely proportional to frequency. 4. Resistance gives rise to the production of Joule heat in a component. In a circuit with pure reactance, there is no production of heat. Exercises Q10, page 305. Show that in an AC circuit containing a pure inductor, the voltage is ahead of current by pi2 in phase. Solution. The following figure shows an AC source, generating a voltage E equals E0 sin Wt, connected to a key K and a pure inductor of inductance L to form a closed circuit. An AC source connected to an inductor. On closing the key K, an EMF is induced in the inductor as the magnetic flux linked with it changes with time. This EMF opposes the applied EMF, and according to the laws of electromagnetic induction by Faraday and Lenz, we have exercises Q11, page 305. An AC source generating a voltage E equals E0 sin omega t is connected to a capacitor of capacitance C. Find the expression for the current I flowing through it. Plot a graph of E and I versus omega t. Solution. The following figure shows an AC source, generating a voltage E equals E0 sin Wt, connected to a capacitor of capacitance C. The plates of the capacitor get charged due to the applied voltage. As the alternating voltage is reversed in each half cycle, an AC source connected to a capacitor. The above table gives the values of E and I for different values of omega t, and the following figure shows graphs of E and I versus omega t. I leads E by a phase angle of pi2 rad. Graphs of T and I Venus Wt for a purely capacitive AC circuit. Exercises Q12, page 305. If the effective current in a 50-cycle AC circuit is 5A, what is the peak value of current? What is the current 1/600th after if was 0? Solution. Exercises Q13, page 305. A light bulb is rated 100 W for 220 VAC supply of 50 Hz. Calculate A. Resistance of the bulb. B. The RMS current through the bulb. Solution. Exercises Q14, page 305. A 15.0 microfarads capacitor is connected to a 220 V, 50 Hz source. Find the capacitive reactance and the current RMS and peak in the circuit. If the frequency is doubled, what will happen to the capacitive reactance and the current? Solution. Exercises Q15, page 305. An AC circuit consists of only an inductor of inductance 2H if the current is represented by a sine wave of amplitude 0.25 A and frequency 60 Hz. Calculate the effective potential difference across the inductor pi equals 3.142. Solution. Exercises Q16, page 305. Alternating EMF of E equals 220 sin 100 pi t is applied to a circuit containing an inductance of 1 pi Henry. Write an equation for instantaneous current through the circuit. What will be the reading of the AC galvanometer connected in the circuit? Solution. Exercises Q17, page 305. A 25 microfarads capacitor, a 0.10 H inductor, and a 25 ohms resistor are connected in series with an AC source whose EMF is given by E equals 310 sin 314 T volt. What is the frequency, reactance, impedance, current, and phase angle of the circuit? Solution. Exercises Q18, page 305. A capacitor of 100 microfarads, a coil of resistance 50 ohms, and an inductance 0.5 H are connected in series with a 110 V 50 Hz source. Calculate the RMS value of current in the circuit. Solution. Exercises Q19, page 305. Find the capacity of a capacitor which when put in series with a 10 ohms resistor makes the power factor equal to 0.5. Assume an 80 volts 100 Hz AC supply. Solution. Exercises Q20, page 305. Find the time required for a 50 Hz alternating current to change its value from 0 to the RMS value. Solution. Exercises Q21, page 305. Calculate the value of the capacity in picofarad, which will make 101.4 microhenry inductance to oscillate with a frequency of 1 MHz. Solution. Exercises Q22, page 305. A 10 microfarads capacitor is charged to a 25 volt of potential. The battery is disconnected and a pure 100 meters H coil is connected across the capacitor so that LC oscillations are set up. Calculate the maximum current in the coil. Solution. Exercises Q23, page 305. A 100 microfarads capacitor is charged with a 50 V source supply. Then source supply is removed and the capacitor is connected across an inductance, as a result of which 5A current flows through the inductance. Calculate the value of the inductance. Solution.